Jai Mataji. We are discussing about photoelectric current, right? First, we have studied about effect of positive potential, effect of negative potential, now effect of frequency. હવે આપણને ખબર છે, we know the basic equation EV0 is equal to H nu minus H nu 0, right? EV0 is equal to H nu minus H nu 0 is equal to half mv max square. આપણને ખબર છે. So obviously, if incident frequency changes, then stopping potential changes. મને ખબર છે, right? We know the experimental setup. This is emitter. If we make incident light of sufficiently high frequency, photoelectrons are emitted. If this is collector plate, this is emitter plate, cathode, anode. And if I keep at a positive potential, so whatever photoelectric current is formed, right? Electron will be attracted by this positive terminal. So whatever, suppose say intensity is I1, 50 photons per second and efficiency is 100%, then 50 electrons when they are reaching at plate A, all the 50 electrons emitted from cathode, જ્યારે અહીંયા પહોંચવા માંડે, that current is called saturation current. Suppose this is saturation current, right? And it is constant. Saturation, it's a photoelectric current versus photoelectric current versus collector potential no graph છે, and this is saturation current, right? It's a straight line. Very good. Now, as I change this incident frequency, this is photosensitive surface. If I change the frequency nu2 greater than nu1, suppose when it is nu1, so obviously we are going to get the stopping potential V01, right? So as we reverse the polarity, હવે અહીંયા નેગેટિવ કરી નાખો ને અહીંયા પોઝિટિવ, so -1 volt, -2 volt, -3 volt, current goes on decreasing and we are getting stopping potential say -V01. Now as nu2 greater, light of sufficient little bit higher frequency than previous one, હવે nu2 greater than nu1 આની પર ઇન્સિડન્ટ કરાવું છું, તો obviously according to this equation now stopping potential will change, so it is -V02, right? And this is for nu1, this is for nu2, right? And suppose if nu3 greater than nu2 greater than nu1, light of nu3 greater than nu2 greater than nu1 is incident, then obviously stopping potential will change, it is -V03. So this is effect of frequency on stopping potential. As frequency changes, stopping potential changes, right? Very good. So let's go through question number 14. Explain effect of frequency of incident radiation. Effect of frequency of incident radiation on stopping potential. We want to study the relation between frequency of incident radiation and stopping potential. આપણે આ બેનો રિલેશન સ્ટડી કરવો છે. Suitably adjust the same intensity, say 50 photons per second, right? Say I am adjusting 50 photons per second intensity, set કરું છું. So this is the saturation current. When this was positive, ત્યારે maximum current જે એસ્ટાબ્લિશ થયો તો એ આ પોઈન્ટ છે, પછી છેડા ઊંધા કરી નાખ્યા, હવે નેગેટિવ કરી નાખ્યા, કરંટને રોકવા માંડ્યા, -1 વોલ્ટ, -3 વોલ્ટ, -4 વોલ્ટ. એ સાયન્સના સ્ટુડન્ટ છીએ, એક્સ એક્સિસ ઉપર y કોઓર્ડિનેટ 0 હોય એટલે એમ કહેવાય આ જગ્યાએ ફોટો ઇલેક્ટ્રિક કરંટ 0 થઈ ગયો, આ જગ્યાએ ફોટો ઇલેક્ટ્રિક કરંટ 0 થઈ ગયો, આ જગ્યાએ ફોટો this potential is called stopping potential. So suitably adjust the intensity of light radiation at various frequency and study the variation of photoelectric current. ચલો ભાઈ, આપણે આને ઇન્ટેન્સિટીને સેટ કરી લીધી અને હવે આપણે ફ્રીક્વન્સી વેરી કરવાના છીએ to carry out its effect on stopping potential and photoelectric current, right? The resulting variation is shown in the figure. We obtain different value of stopping potential, see, but the same value of saturation current for incident radiation of different frequency. ભલે ને મેં nu3 greater than nu2 greater than nu1 ઇન્સિડન્ટ કરાવ્યું, પણ મેં 50 ફોટોન્સ પર આ નથી વધાર્યા. જો 50 ના 500 કર્યા હોત ફોટોન્સ પર સેકન્ડ તો આ પોઈન્ટ ઉપર જાત, તો કરંટ વિલ ઇન્ક્રીઝ. પણ અત્યારે આને આપણે કોન્સ્ટન્ટ રાખ્યું છે અને ફ્રીક્વન્સી ચેન્જ કરી તો સ્ટોપિંગ પોટેન્શિયલ ચેન્જ થયો. The stopping potential is more negative for higher frequency. જો તો nu3 greater than nu2 greater than nu1, right? So stopping potential is more negative, right? Very good. So V03 is greater than V02 is greater than V01 for nu3 greater than nu2 greater than nu1. સાચી વાત? Okay, yes. This implies that greater the frequency of incident light, greater the frequency of incident light, greater is the stopping potential and greater is the maximum kinetic. Obviously it is as greater is the frequency, maximum kinetic energy of electron is more and hence એને રોકવા માટે stopping potential would be more. જો હું આ લાઇટ ની ફ્રીક્વન્સી વધારીશ તો જે ઇલેક્ટ્રોન નીકળતા હશે પ્લેટમાંથી એની કાઇનેટિક એનર્જી વધારે હશે અને એને રોકવા માટે the stopping potential would be more. So consequently we need greater retarding potential, right? તો આપણે greater retarding potential એટલે stopping potential વધારે જોશે. If we plot the graph of frequency of incident radiation and the corresponding stopping potential, જો વાત બદલી છે, આ ગ્રાફ હતો photoelectric current versus collector potential, photoelectric current versus collector potential ની વાત હતી. હવે stopping potential versus frequency, તો કાલનો problem 11.6 યાદ કરો. We have done problem 11.6. EV0 is equal to h nu minus phi 0. So graph of stopping potential versus frequency is a straight line. It's make V0 as a subject, right? So it is h by e nu minus phi 0 by e. So graph of stopping potential versus frequency is a straight line, right? Is a straight line and its slope is h by e. Yes or no? Its slope is h by e. Its x-intercept, its x, we have written everything in knots. Its x-intercept is threshold frequency nu0. X-intercept is threshold frequency nu0. Its y-intercept is minus phi 0 by e. Y-intercept is minus phi 0 by e. Hypothetical. So if we plot the graph of stopping potential versus frequency, very very important graph, then it is a straight line. This is x-intercept and it is equal to nu0, right? It is equal to nu0. Suppose if I change the metal, so for different metal work function is different, so threshold frequency minimum requirement is different, so it is nu0 dash. This is for metal B, but slope is constant for all the metals. See my yesterday's video. For this graph slope is h by e. So irrespective of this emitter metal, irrespective of the metal, slope is same h by e. So all the graphs are parallel, right? So this is for metal A, this is for metal B. Here slope is h by e, x-intercept gives you threshold frequency, and hypothetical y-intercept is minus phi 0 by e, right? Very good. So this graph shows that the stopping potential V0 varies linearly. Obviously it is a linear graph with frequency of incident radiation for given photosensitive material. There exists a certain minimum cutoff frequency nu0 phi 0. So nu0 minimum cutoff frequency કે જ્યાંથી ગ્રાફ કે ફિનોમિના સ્ટાર્ટ થાય છે of incident radiation, but is independent of intensity. આ threshold frequency ને કેટલા ફોટોન્સ ભટકાડો છો, ઇન્ટેન્સિટી એટલે નંબર ઓફ ફોટોન્સ પર સેકન્ડ, થ્રેશોલ્ડ ફ્રીક્વન્સી ને કેટલા ફોટોન્સ ભટકાડો છો એની હારે રિલેશન નથી. For a given frequency of incident light lower than cutoff frequency, માની લ્યો કે your incident light is less than nu0, then photoelectric effect will not take place. Then photoelectric emission is not possible even though intensity is whatever higher is the intensity. જો તમારી very very important point, બોક્સની ઉપરનો સેકન્ડ પોઈન્ટ બહુ ઇમ્પોર્ટન્ટ છે. આ મેટલ ઉપર if you are imparting the light of frequency less than your minimum requirement, તો ઇલેક્ટ્રોનનું ઇમિશન નહીં થાય. Photoelectrons are not going to emitted whatever may be intensity, 5000 photons per second, 5 lakhs photon per second, 50 lakhs photon per second, ગમે તેટલી intensity ભટકાડશો અહીંયા light. પણ if nu is less than nu zero, photoelectric effect is not going to take place. The minimum cutoff frequency nu zero is called threshold frequency, and it is different for different metals, right? Also go through some important notes. Different photosensitive material. This is not part of answer. This is not part of question number 40. Answer of question number 14, right? Different photosensitive material respond differently to light. Obviously it is. એકની એક લાઇટ હોય એની હારે અલગ અલગ મેટલ એને અલગ અલગ રિસ્પોન્સ આપે. Selenium is more sensitive than zinc or copper. The same photosensitive substance gives different response to light of different wavelength. Obviously it is. એકની એક મેટલ હોય તો એની પર જુદી જુદી ફ્રીક્વન્સી કે વેવલેન્થની લાઇટ ભટકાડશો તેનું બિહેવિયર અલગ અલગ હશે. સર્ટેન ફ્રીક્વન્સી લેસ ધેન ન્યુ ઝીરો હશે તો એના માટે ઇમિશન નહીં થાય. જે ફ્રીક્વન્સીની મિનિમમ રિક્વાયરમેન્ટ કરતા તમે વધારે ફોન કરો તો ઇમિશન થશે. For example, UV light gives rise to photoelectric effect in copper, while green or red light does not. यहाँ अंडरलाइन करजो કે કોપર ઉપર UV light ફોલ કરાવશો તો photoelectric effect will be seen, but green or red light fall karavso so you cannot observe photoelectric effect. Not that in all the above experiment it is found that if frequency of incident radiation exceeds the threshold frequency, the photoelectric emission start instantaneously. This point is very very important. If my minimum requirement is fulfilled, say this is photosensitive surface, and if we incident the light of sufficiently high frequency, that is nu greater than nu zero, then photoelectrons are emitted instantly, spontaneously within 10⁻⁹ second. Mind well, જો તમારી ઇન્સિડન્ટ લાઇટની ફ્રીક્વન્સી તમારી મિનિમમ રિક્વાયરમેન્ટ કરતા વધારે હશે તો ફોટો ઇલેક્ટ્રોનનું ઇમિશન will take place just within 10⁻⁹ second, right? So emission starts in a time interval in order of 10⁻⁹ second or less. यहाँ पर underline करजो. This data also may be asked as MCQ, right? So this was question number 14, right? Thank you. Jai Mataji.